Welcome, and thanks for welcoming me. And we're going to talk about product strategy and design strategy reasons why projects and products fail from a design point of view, because we want to know how it affects our design and the strategy that goes hand in hand with design. What I'm going to try to do for the next hour is to be roughly half and half talk and then Q&A. So we hope to leave a good amount of time near the end for Q&A in Remo. But first, let's talk about how to answer the question. When you're starting a new project, you have a new idea for a product, or you're being asked to adopt somebody else's product or fund somebody else's project, how to ask and answer the question, well, why is your thing going to succeed when, I've seen a few things that look a lot like it and they haven't succeeded in the market? What makes yours different? That's the question that we're going to focus on answering. Because overcoming that history and differentiating yourself, not just in speaking to others, but to know internally, why am I strategizing and designing for success, is important as we think about what our product is going to do. Now, we're not going to talk about many of the reasons projects fail. We're not going to talk about there wasn't enough funding. The team was inadequate or the wrong kind of people, that product quality was low, the rollout advertising didn't happen, and those kinds of things, because those aren't directly intertwined with the design and strategy of a product's design. And usually these ones are fairly obvious things that you see in a post-mortem. Well, why didn't it succeed? Okay, one of these things. What we're going to focus on instead is what are the strategy differentiators that affect design. And it's primarily going to be talking about compatibility, but we'll see also how the value proposition and availability feed into compatibility and how these things are related. But we're going to spend most of our time on number 3. So let me first define what a new thing is. So the title of this talk is Bridge to New Thingia. And yes, that's a riff off Bridge to Terabithia, because we're going to see there's a bridge involved. We're going to talk about compatibility. But what is new thingia? What is the place that we want to get people to? I'm going to define a new thing as one of two things. It can be a brand new competing product. Many of our examples will be from programming languages. And there we see things like D, Go, Swift, Rust, other new programming languages. And those are easy to see they're a new thing because they have their own name. But a new thing can also be the next major version of an existing product. And think about it. If you have an established product in the marketplace, your biggest competition usually, if you're the leader, is your previous version. And sometimes you have to do convincing and to be persuasive to get customers to upgrade from that and make sure they have a reason to. So every major release of the C++ standard, its major competitor is not some other named language right now. It is the previous version in the field of the standard. And a good example of why this really matters is if you look at Visual Basic 6. It was a very, very popular system that had many strengths and some flaws. But if you go to Wikipedia today, you will find 2 articles to this day about Visual Basic. Why? Because after Visual Basic 6, the Visual Basic name continued to be associated with a product that was incompatible and that was actually different, to the point where they still have the same name, but they're very different products. Witness, they have their own Wikipedia pages, even though the product has the same name. A new thing doesn't depend only on the name, so it can be version next of the same brand product. So let's first talk about the value. The first question we have to answer is, why should somebody be interested in the product that I'm designing? There's been a lot written about that, and it's all about the value proposition and the elevator pitch. So let's just make 1 or 2 points about the key things in the value proposition. If I'm going to be able to have that elevator pitch where I get in the proverbial elevator with the executive and I have about 30 seconds in that elevator ride to explain to my executive what's so exciting about my product, how am I going to do that? The easiest, the simplest way is by saying, hey, this thing you already have? we're going to solve this known pain point or these known pain points with that. Now, as soon as you do that, you haven't had to explain your product from scratch. You've directly connected it to an existing well-known thing. And by anchoring it, you don't have to explain the common fundamentals, the general problem to be solved. And you've also related your thing and oriented to an existing thing. And you've been able to clearly say, and we're going to solve these known pain points. If you pick real pain points, you won't have to explain them. That's how you give a 30-second elevator pitch. You refer to something the person already knows well, an old thing that they know, a product in the field. You refer to pain points they probably already know well, so you don't have to explain them either. You just have to name them. And you say, I'm going to solve that problem. That's how you give a 30-second pitch without talking a mile a minute. And you're showing how I'm going to build a bridge across this chasm in this place to bring you to this shining castle on the hill. So for JavaScript, it was well known that JavaScript is a very useful language and a foundational language to our modern web. It is also well known to be very bloated, intricate, have lots of corner cases. And if you just look at the books, JavaScript, the definitive guide, JavaScript, the good parts, here's a well-known pain point with JavaScript: complexity, the learning curve, the amount of stuff you need to know. And more than one language has come along to try to solve that problem. So both Dart and TypeScript have come along and said, you know what, JavaScript, you know it well, it's great. We want to solve this problem, the pain point of the language's size and complexity and usability. And that helped them to very easily in 30 seconds, in fact, we just did it in 10 seconds, explain why these languages. Now, these two examples were not equally successful. We'll come to that in a moment. But JavaScript is not alone here. You may know of other languages that also have a good parts version where you can point to the same pain point and say, you know, this existing useful language, the same opportunity exists here to solve the problem, this pain point here of complexity. So once we've articulated the value, the proposition, that 30-second elevator pitch, which we can do best by saying, you know this old thing, we're going to solve these known pain points. Now you've got people interested. How can they start kicking the tires? By making it available. If you tell people about this great idea and they say, great, where can I download something to try it out? And you say, we'll have that in about a year, you're not going to get very far. Or it's not available on your platform yet. So we want to design for having our new thing be available. And the requirement is basically, we want either initially or in the medium term, there's no design obstacle for our new thing to be available on every platform in every place where old thing exists. That means any user of old thing can try out new thing and start using it in their projects. It works on my platform. And I have to at least be able to add it in the same place where I have an old thing project in order to be able to try it out and compare. So here are some examples from programming languages. C came along at a time when every major system, every major hardware system had its own programming language for systems programming. There was no such thing as a portable language that gave you high performance. C was the first to come along and try to solve that problem. And we can argue about, did it just work on all PDP-like architectures and then everything became PDP-like? Nevertheless, C did something that a lot of people told Dennis Ritchie could not be done, and that is create a single language that could give you portable performance where you write the same source code and you could translate that to an efficient binary on multiple machines, different architectures. He did that, and that affected the design, but notice how it ties in with availability. That means regardless of what kind of major computer I was using, I could get a C compiler and I could try it out because it supported a range of different hardware. It didn't support just one particular hardware from one vendor. C-front, CPython, still one of the main Python translators, and TypeScript all followed a very similar model for availability. CFront compiled C++ to C, which means it worked anywhere a C compiler existed. That means as C was the old thing, and now C++ was the new thing, seeking to get interest. Well, if you like the ideas of C++ and you say, where can I try it out? Well, if you're already using a C compiler, you can try C++. The reason is CFront itself was written in C++, but it translated programs down to C so that you could take any C++ program, run it through CFront, and then through the C compiler you already had, and be able to try it out, get an executable. But if you were on a system that C++ itself wasn't available on yet, CFront itself was written in C++, could be compiled down to C, and you could take that and compile that with your C compiler and bootstrap your way to a C++ environment. To this day, CPython is written in C. It's available anywhere where C is. Every TypeScript program compiles to JavaScript. It's available anywhere JavaScript is. So in each case, new thing is available in all the places old thing is, and that enables people who are interested in your value proposition, makes it available to them to try it out, kick the tires. Now, Swift and Roslyn are two examples that didn't do it at a language and a compiler level so much. They did it sort of kind of at the IDE level. So Swift was available out of the gate to every Xcode developer on every platform Xcode supported for Objective-C. And now it actually supports more platforms than Objective-C. But it was available. If you were an Objective-C developer and you liked what Apple told you about this cool new Swift language, you just had to have the latest Xcode, which you were already using for Objective-C, and Swift would work on your platform so you could try it out. Roslyn, which was the rebuilding of the .NET compiler so that you could do things like static reflection and a great toolability story. That's a great value proposition. How do I try it out? It was available on to every Visual Studio developer on every platform, Visual Studio and Visual C#, the compiler it replaced, supported. And you could still have your own Visual C# compiler to compile to native code, to compile to .NET assemblies, and use Roslyn for your IDE, but Roslyn could be there. It was available. I want to emphasize all of these were by design. These were not accidents. They affected product strategy. They created constraints in how you built these things. Roslyn had huge compatibility constraints from the very beginning of the project, and that slows down development. It means you are doing more work. It's not free. You are paying for it in design trade-offs, in overheads for quality, and in this case, compatibility gates. But because of that, Roslyn made itself available, but it wasn't an afterthought. It was by design in all of these cases. Both value and availability are related to compatibility. So let's spend the rest of our time talking about the compatibility bridge, because this is how you then, after they've kicked the tires, you bring people to be able to adopt at scale your new thing. And this is a key thing and a key place where people get it wrong. And it doesn't mean they won't succeed, but as we'll see, it means it will cost them a decade. And that's an empirical observation. Let's see examples. When you're delivering a new thing or you're adopting it, you're going to be able to put forth some effort and then see some value. What do you want that adoption function to look like? Do you want to have to put forth on the left, option A, lots of effort before you start seeing value, and then maybe you see a lot of value all at once, but it took a lot of effort where you didn't actually see anything, and that you had to put in upfront before you saw any value? Do you want A or do you want B, where you can put in a little effort and start to see some value, put in a little more effort, see more value? That ramp, B, is the model that is going to make products succeed where others have failed. And the basic requirement for that is high fidelity interoperation with old thing. The very minimum bar is for it to be in the one direction, where any new thing, in this case, in a case of a programming language, any new thing code can seamlessly use old thing. code written in the new language can seamlessly invoke code written in the old language. Now, a good story is if I have an old language project that I can put in the new language in that project and use it side by side, say in separate source files. So I can add to a C++ project or C project, I can add a .cpp file and start seeing some benefit. The holy grail, though, is to be able to say, I can start using the new language in just one place, in just one line of code, maybe even in old language file, and start to see benefit. And in case that sounds like too much of a holy grail, it's been done repeatedly. That's what C++ did for C. You could largely, still to this day, largely take any .c file and compile it as C++, and you can add one class and start seeing benefit. The rest of your code compiled, you can still call it from your C++. Oh, but now look, I have an encapsulated class with private data. I've seen some benefit by just writing a line or two of code. The same thing is what TypeScript did for JavaScript. Every TypeScript program is a JavaScript program, and you can, by design, rename any JavaScript file to .typescript, add one class, and start seeing benefit. That gives you the smooth adoption function. And again, it's by design, because for that to be possible, placed a great burden and a great restriction on the designers of C++ and TypeScript. C++ to this day carries the baggage and the weight of the C compatibility that makes that story true, but we wouldn't be talking about it today if it hadn't done that, very likely. Similarly, TypeScript took off as fast as it has, in large part because of that compatibility with JavaScript. That was a very great constraint. Anders Hausberg could have designed another scripting language equally technically good as TypeScript, and even better in many ways, if there wasn't the JavaScript compatibility restriction. But it also would have been adopted far more slowly and because it would have been an incompatibility story rather than a compatibility story. So ramps are great. They're not just for old folks. Industrial strength use of ramps exists because it makes our lives easier to get things from point A to point B. Now, we talked about C++ and TypeScript, this compatibility by design, because every C program is a C++ program, largely true, and C++ code from the beginning has seamlessly been able to invoke the C optimizer and linker. They didn't have to rebuild their entire tool chain. Bjarne, by creating CFront, leveraged the heck out of all the existing infrastructure that was already built into C. Instead of competing with it by being compatible, he enabled us to reuse it. Same thing is true with TypeScript. But now when we talk about Swift and Roslyn, I just want to point out how important this is and how it affects design in a different way, because Swift and Roslyn are a bit different from what TypeScript and C++ did. With Swift, there's a bidirectional high-fidelity interop where Objective-C can call Swift and Swift can call Objective-C. And that is because two basic things are true. There's others, but the two primary design constraints are Swift uses essentially the Objective-C object model, and it uses Objective-C lifetime model, which is reference counting, including ARC, the automatic reference counting model in Objective-C. It also uses modules, the same modules in Swift and Objective-C. This was not an accident. In fact, when ARC first shipped in Objective-C before Swift was announced, it was already designed with Swift in mind. Objective-C modules were designed with Swift in mind before anybody outside Apple knew what Swift was going to be. So you could see Apple already building that adoption ramp even before announcing new thing, because they had control of old thing and were able to make old thing meet it. You have less control when you're building a new thing externally, entirely externally from old thing. But in both cases, it affects design. Swift could have been, in many ways, a better language for many things if it didn't have this backward compatibility constraint. It also wouldn't have been as interesting or as used. Similarly, Roslyn, as I mentioned, had strict backward compatibility tests baked in from the very beginning and had to be adhered to rigorously from the beginning of the Roslyn project to be able to replace the C# compiler that it was replacing. And that was a compatibility constraint that added cost, it added time to the project, and it constrained the design. But it also enabled Roslyn to be transformational and adopted way faster than it could possibly have been if it hadn't incurred those costs. It's a design strategy and a strategy for design that create attacks, but it's a cost that we get a specific benefit for, and it's conscious, and it has to be from the beginning of the project. It is very hard to retrofit. If you hadn't designed Roslyn to be a C# drop-in replacement, a compiler replacement from the beginning with compatibility tests, if you hadn't designed Swift to be an Objective-C compatible replacement with the same object model and reference counting infrastructure, lifetime modules from the beginning, and accepted those constraints and lived within them, you wouldn't have been successful, and you wouldn't have been able to backfill later. We talked a bit about TypeScript. You might have mentioned, remember, we also mentioned Dart. Dart also had the same value prop as TypeScript, which is, look how complex JavaScript is compared to JavaScript, the good parts. We're going to solve that problem. So Dart and TypeScript had very similar basic value propositions. We don't hear very much about Dart today, and its adoption was greatly slowed for several reasons, but one major one was the lack of compatibility. Dart was not JavaScript compatible. It had very minimal ability to call JavaScript. To this day, there are open, here's a screenshot from GitHub, there are open issues for JavaScript to try to improve interop, and notice that the words they use in those two paragraphs at the bottom of the screen are very similar to trying to get the value propositions that TypeScript had for JavaScript, that C++ had for C, that Swift had for Objective-C. But those three were successful because they had it from the beginning to design, to guide and constrain their design as a stake in the ground up front. It is very hard to go back later. The reason is because if you don't have a compatibility story up front, you end up on a wrapping strategy. Those are the two major paths, and there are flavors. But you can either call the existing thing directly, or you can't, in which case you end up wrapping things, and you have an impedance mismatch on the boundary. And that boundary can look different in different, as you're bridging different gaps, different things, different new language, old language combinations. But it's basically a wrapping strategy. You got to wrap it to be able to use it. C++ CLI, Python 3, C++ WinRT, they all fall into this category. The same thing with D and its compatibility for calling C++ types. It's a wrapping story. And that's the story, the plan that Dart is on. You can't switch back. You can't go back in time and change your design to be object model compatible and bring compatibility back. It has to be part of the initial design, which means to backfill it basically means to start over. It would require basically a reset. Here's an example from Python, and this can help us start to quantify what the cost is of compatibility. So Python 3 took a source-breaking change in 2008. You cannot compile Python 2 code as Python 3. Yes, there are quite a few migration tools that really help make that transition. But something as basic as what is the type of 3/2 and what is the value of 3/2 has a different answer in Python 2 than it does in Python 3. There are other examples, but I find that one to be a useful basic example of, oh yeah, well, if I can't compile 3/2 and know what the answer is, I'm in an incompatible language. Even if it's still called Python, it might as well be called abracadabra because it is an incompatible different language. Well, what happened? Well, 9 years later, as of 2017, most Python code was still written in the intersection of Python 2 and Python 3, which may sound good until you realize, wait a minute, that means they aren't using any Python 3 new features inherently. Now, they got over it and that changed. As of this year, as of about 11 months ago, Python 2.x was frozen. It is unsupported. But at that time, about 10% of Python in the world was still written in Python 2. Think about what that means. Using an end-of-life product that is no longer supported even for, if I remember correctly, for security fixes. So 90% adoption is great, but even so, to have 10% as of a year ago of your user base still in that unsupported old thing is a problem. And it shows that this took a decade, in this case, 12 years, to get to 90+% adoption. Now compare that to the previous cadence. Previously, for Pythons 1, 2, and 3, those were released 8 years apart. So it's not just that it took 8 years to adopt each one. Each one was adopted enough to freely be able to go to the next major release within an 8-year period. 12 years after Python 3, we're still talking about just finishing absorbing Python 3. We're not talking about shipping Python 4 yet. Now, it's not just Python. Even other languages like C went through this problem. So in the late 1990s, the C committee was very small. It was dominated by a few special interest people who, because the committee was small, were able to get their way and add features that it turns out that the larger community wasn't all that interested in, including compiler vendors for C. So there were several features in C99 that were standardized, but were not widely supported in compilers for quite a few years. In fact, we mentioned CPython, which compiles to C, Python to C. It itself, as a C program, is only allowed to use a very small number of C99 features as they're proven to be widely available in compilers. That's today, 20 years later. That is still true. So what happened at the halfway point between now and when C99 shipped, the C11 standard came along. So here they are, 12 years later. They added a new thing. They added the idea of a conditional or optional feature. And they applied that not to just some new C11 features, but also retroactively to C99 complex and variable length arguments, variable length arrays, because those were controversial features that people were not implementing widely. So they went back and made it optional. It is easier to write a conforming C11 compiler than a conforming C99 compiler, because you can just say, macro define, no, I don't support that feature, and you're done with the optional features. This even happened a little bit with C++, because C++ is very backward compatible, but every so often we took a breaking change, and we did that with stood string. In 2008, we adopted a change which shipped in the 2011 standard to say, no, stood string cannot be reference counted. But this isn't some corner case. This is the standard string type. We said, it can't be reference counted. And people agreed to that, understanding it would be an ABI breaking change on some platforms. But that didn't mean you could ship it right away. It wasn't until 2015 that in GCC, there was a conforming stood string being shipped by default. Then it was gradually adopted platform by platform, and it wasn't until last year that one major platform, Red Hat Enterprise Linux, first turned on the new conforming string by default. Did you notice how many years that was? Interesting how that number keeps coming up. This is what a decade looks like. If you put the calendars for 10 years and 12 months side by side, C99, it took about 12 years to fix the incompatibility mistake of the VLAs and complex. 10 years after they shipped, 12 years after they shipped, the C standard walked them back to be, we weren't actually that serious about them. They're optional. C++11 string stayed in the standard with its ABI breaking change, but it took about 11 years to reach some popular platforms. Python 3, from the time it was released to the time it got to 90+% penetration, was about 12 years. If you don't build a strong backward compatibility bridge, meaning that new thing can seamlessly call old thing, doesn't mean you won't succeed. You may still succeed, but it's going to take you a decade longer, absent other forces, because there are other mistakes we could make or other things that we can do to force people to move even if they're not ready, if we control a platform, for example. But generally, experience has shown it's going to cost adoption a decade. Now, like I said, you might succeed anyway, but not only does this extra decade slow down your adoption, it also increases your risk because it means you have to keep surviving and getting some adoption and some traction for a longer period of time before you get to the hockey stick. And you have to have a longer time you have to survive. That adds risk to a project because your project needs to survive that long to survive at all. So when we talk about an incompatibility, it's like taking a sharp turn. Every time you take a sharp turn, some people fall off, and occasionally you stop making progress entirely if too many people fall off or if the truck turns over. So let's talk about two pitfalls in conclusion. Two specific things that create a form of incompatibility that create that step function for adoption. One is heavy annotation, and heavy can be surprisingly low. So if you ever had a product or tried to design a product and convince people to adopt it that said, oh, but you have to annotate your code. How much? Oh, 1 every 10 lines. Excuse me? No, thank you. Oh, just 1 every 100 lines. That's still way too much. What does that mean for my million-line of code project? So even 1 line change per 1,000 lines of code is often viewed as a heavy number. Now, if in addition, one of the ways that you can get this annotation requirement is when annotation has to be viral. So I can't just annotate one place, I have to annotate others. So say I have a safe C dialect where I can annotate a function as safe. Wonderful. But what if the rule is I can only call other safe functions from inside my safe function? Well, then anything I call has to be annotated. Well, anything it calls has to be annotated for it to be annotated safe. So in that kind of case, if you have like a red function, like a safe function, can only call other red functions, you need to do a bottom-up annotation of your call trees. That's going to hurt your adoption. That's not compatible. That creates that adoption step functions because it requires a lot of work before you can start using it and seeing benefit. But you can also get viral upward. So Java found this out with checked exceptions. If you have to say in Java, oh, I can only call a red function from other red functions. I can only call a function that throws X and Y from a function that also advertises it throws an X and a Y. Then I have to upward annotate the call path. In order to call this function, I have to annotate the caller function. In Java, people voted with their feet and largely just turned off the feature by saying, oh yeah, throws exception. I just throw the base class of all exceptions. So I'm just basically not going to use the checked exceptions feature. Some people do use it. I'm not saying it's not used. I'm saying that most people voted with their feet and just turned off the feature because they could. We see the same in safe C dialects. So both Cyclone and C-Cured had this annotation problem. C-Cured lasted long enough to have a follow-up paper, type-safe retrofitting of legacy code in 2005, where one of the things it would do is infer the annotations. And newer efforts, such as CheckC from 5 years ago, David Tarditi, right up front is doing that value proposition thing we talked about at the beginning. It's saying it's answering the question, how are you different from Cyclone and C-Cured that have failed? Because CheckC sounds a lot like them. Because we are going to bring you across this bridge. We're going to solve this pain point. We're going to have backward compatibility and no annotation requirement, incremental conversion. So Tarditi answered the question, how am I going to be different? Why might I succeed when Cyclone and C-Cured have failed? By saying the value proposition, I'm going to solve the safety problem, but without viral annotation. I'm going to solve the pitfall with these other two of that viral annotation and other incompatibility. And I'm going to have a strong compatibility bridge where I can incrementally convert a C code base. I can make a small change and start seeing benefit. That doesn't mean that CheckC will succeed, but it shows that they're doing it right. They're applying the principles of this talk to answer the question, why should you succeed when these others that look a lot like you failed? Here's what's different. Value, availability, but especially compatibility. The second and last pitfall is false friends. Remember 3/2 has different answers in Python 2 and 3? That means you have to start making hard choices. You either don't allow them in the same source file, which is what Python did, or you allow them in the same source file, but then you have to have regions of code. Well, I'm going to say Pragma version 2 region or a Pragma version 3 region. That makes things harder for programmers because they still can't reason about this piece of code in the source file just looking at it without looking around to see what mode am I in. And it creates similar problems for refactoring tools and other automation if the same code can mean different things, especially inside the same source file. That's what we call a false friend. Looks familiar, but means something different. So then, how do we answer the question, why will your new thing succeed when these others that look a lot like it have failed? And once we take aside the usual answers of funding, of the team, of marketing, and we look at what are the design and strategy reasons, they come down to these three things. The value proposition should clearly articulate how it's going to solve a known pain point with old thing. And if it's a real pain point, it will need very little explanation. It needs to be available where old thing is used so people can start, who are interested, can start trying it. And that affects design. It has to be designed for from the start, just like the C front compiler architecture was. And finally, compatibility. Seamless backward interoperability with the old thing. Dart and others, and D and even Rust show that this is very hard to back into later. It has to be an explicit design goal from the start. If you don't do this from the start, you may still succeed. Doesn't mean you'll fail, but it will take you 10 years longer to get the adoption than you could have had. At least you want to have the good story of I can use old thing side by side in a new thing project, like a new .cpp file in a .c project. The holy grail is I can write one line of code if it's a programming language and start to see benefit. I can write one line of C++ code in this C file, renaming it to .cpp and writing one line of code and start to see benefit. Sometimes I'm asked, well, what will the successor of C++ be? Will there be a successor to C++20? Some new language, there's lots of work being done in new languages. D and Rust are common examples, but not the only ones. And first of all, language innovation is a good thing. All of these languages are doing really interesting work that I think benefits the world, regardless of whether they succeed broadly or not, and can inform the work being done in adjacent languages like C++ and others. But if languages like those haven't yet displaced C++ in the marketplace, what's the difference? Well, there is actually one language that has successfully displaced C++ in the marketplace, but it's always C++ next, because remember, the next release of a major product has as its primary competitor the previous release already in the field. So we're shipping C++20 right now. Its primary competitor in the field is C++17. C++17's primary competitor was C++14. And each of those has displaced, or we hope with 20, will displace the previous, primarily because it's solving problems, it's available where C++ previous was, and it's got seamless backward compatibility. If a new language wants to have a similar uptake, it should have the same compatibility bridge and have seamless interoperability with C++ by design. If it doesn't have that, it doesn't mean it will fail, but it will take a decade longer. That's what it takes in the empirical observation of what languages have done that have gone before. Now, there are costs. You have to know the C++ object model. You have to be able to somehow inhale header files or do something to be able to seamlessly call functions that are written in C++, not just C. But if you don't have that, you have to be on a wrapping plan, on a Dart plan, not a TypeScript plan. So when we think about that shining city on the hill, we give that value proposition of, I'm going to solve these problems for you. That's the elevator pitch. I'm going to solve these pain points. We then make it available, all the places old thing is used, and we give a compatibility bridge to new thing. And if we can do that successfully, where a new thing can seamlessly be used side by side with and call old thing or better, then we have a good answer to why will your new thing succeed when others that superficially look a lot like it have failed, because we've designed for the compatibility bridge to be able to make old thing and new thing work together and bring people to the new thing world.